This video will discuss exoplanets, extrasolar planets, planets orbiting other stars, and discuss methods of detecting them, direct view, Doppler Shift, transit method, and there'll be a few more on graphs, but you should go to the webpage at exoplanet.eu. So it's a European astronomy page that tells us there that as of November 2014, 1,850 confirmed planets. So how do we go about finding a planet? Well, you might think we take our telescopes and we look around other stars and try to observe planets around other stars. There's a tremendous problem. The star systems are very far away from us, and the light that comes to us from the planet is reflected light from the star. This light is very, very dim compared to the star itself, and unless the star is very close, the planet is going to be just in the glare of the star's light, unless we're clever. And two ways to be clever is to observe in the infrared, not in the visible. Stars are dimmer in the infrared than in the visible, but planets emit infrared light. They get warmed up by their host star and then send infrared light back out into space. So that will compensate a little bit. Not totally, not nearly totally, but it does help a little bit to observe in the infrared. Another method is, if this star is close enough to us, it's possible in the operation of the telescope that the light from the star can be blocked, can be obscured by a piece of equipment in the telescope, and then the light around that blocked star can be observed. Or digitally now, the light from the star can be subtracted from the image, and perhaps the planet's light will be able to be seen. So direct view, that's one possibility. And here's an image. And many people believe this is a body in orbit around another star. There's a little controversy, but so we have the object located 2004, 2006, 2010, 2012, and it's in an orbit around this star. And this star's light has been blocked, and it's not a brilliant image of a planet around another star, but there is this brightness that is tracking in an orbit around another star. So we cannot make out surface features at any level here and see much detail, but it looks to me that we are having a direct view of a planet in orbit around another star. Another situation here with the very bright image of the star itself with the Hubble Space Telescope, but doing processing to remove the star's light, these blobs are found, and again they're in motion around this central star. And if make a drawing, they can be plotted in orbit around the central star. So that's images of exoplanets. What might happen in the future? Well, if we can get the telescopes a little bit better to isolate these objects and gather enough light, then the spectra of light reflected by the planet can be detected, and that light can be analyzed to see if the planet has an atmosphere, see if it has water, see if it has oxygen, and that would be very important in the search for other life in the universe. So these search for planets that would have conditions where life might exist. Second method, the Doppler Shift. The Doppler Shift. As planets move around a star, the planet's gravity does pull on the star. The star is extremely massive compared to the planet, so the star does not move much. The planet is doing most of the motion in its orbit, but the star does move slightly, and it moves enough that astronomers can detect the speed changing of the star away from us and towards us. A very small shift, but the wavelength undergoes a Doppler shift. Whether the object is moving towards us, we get the blue shift, or moving away, a red shift. And astronomers can measure this periodic shifting of the wavelengths of the spectral lines and determine that there are objects in orbit around the star. So it does have a preference for finding large planets because the large planet has more gravity. It makes the star move more. And it does have a detection method where we need the Earth to be in the orbital plane of the planet to get the best signal, the best motion of the central star. If you recall, the Doppler shift only gives us an effect if the object is moving directly towards us or away from us. So if we happen to be looking face on to the solar system, that'll be good for the direct imaging of the object, but won't be so good for Doppler shift because the star won't move towards us or away from us. It'll move kind of up and down as we look at the sky, and that doesn't create a Doppler shift. Then the transit method. If an object goes in front of its host star, there's less light that's going to come to the Earth. So we call this a transit. When the planet passes in front of a star, we have a transit. So there's also a detection problem here, that we need the planets to orbit in such a way that the Earth is near the plane of their orbit, so that they will pass in front of the star. Again, if we're looking top down on a solar system, the planets in our view are going to go around the star, but they won't pass in front. The Kepler spacecraft, and there have been other missions that are using this method to detect planets around other stars. The Kepler spacecraft, very, very successful. It had some problems with its pointing system and stopped that principal operation in 2013, but it's running again and taking observations. Astronomers have figured out a way to still make use of this Kepler spacecraft and do useful astronomy with it. So while it was running full steam, it monitored continuously the brightness of 145,000 stars. Now, we're obviously using digital methods for this, not one star at a time, but taking an image of a whole section of the sky and comparing that brightness continuously to see if the brightness changes. If there's a case where a single star dims down and then brightens back up, and then several weeks later dims down again, brightens back up, and then the same amount of time, a third time the dimming occurs, then astronomers can be confident that there's a planet orbiting the star, and it's not just a star spot, that causes the light to go dimmer. So there's over 2,000 planet candidates, and great success. So here's kind of the scheme of things. There is a little bit of a preference for a larger planet being detected than a smaller planet. A larger planet covers more of the star and gives a better signal, but Kepler can detect Earth-sized planets going in front of other stars. You just see here some different data being presented. Something that's interesting, this is the amount of time for the dimming to repeat. It takes the Earth 365 days to orbit the Sun. So if some other civilization is looking at the Sun for a change in brightness, they're going to see Mercury and Venus move across the Sun more rapidly. The Earth once every 365 days if they use the time period of days. So little preference here for detecting objects that are closer to the star. They're going to cover up more of the area from our point of view, and preference for larger planets. So 2011, taking a look here, this is the time for the planet to move around its star, and it doesn't even go out to 365 where the Earth would be located. And then the size relative to Earth, you can see most of the detections are for objects sort of Jupiter size, Neptune size, a few Earth size and a few smaller than the Earth, but there is a preference for larger objects. Little histogram here, 2012, Earth size 246. That's not a bad number of Earth-sized planets seen around other stars. And now 2013, 351 Earth-sized planets as of January 2013. And then some drawings can be made. There are systems where there are multiple planets around a single star. The Kepler 62 system showing its objects laid out here, and our solar system for comparison laid down here. And notice that some of these track in what's called the habitable zone, basically where the temperature is such that there can be liquid water. There's more to it than that, but the one prime characteristic is the temperature where we'd have liquid water. And it takes a certain distance away from the star to produce that temperature. And then a fairly recent, according, I'm recording this video in late November 2014. So here's a plot from 20th November 2014 showing you these different methods of detecting the planets. The red dots, this is Doppler Shift. The green, that would be transits with Kepler or other measurements looking for the brightness change in a star. Microlensing, as a planet goes in front of a star, a distant star, it can change the brightness of that star in a special way. Direct imaging, you see some of those out here. They're the ones that are further away from their central star, is easier to do. And timing variations, dealing with orbits. So I just want to focus on these two, the radial velocity and the transits. The Doppler Shift method, and then the Kepler type method of watching how the brightness of a star. So if you look at the period in days, it's a logarithmic scale, but you should look for 365. That would be the Earth's orbit. So 200, 300. So right around in here, if these stars had the same mass as the Sun, then we would see here a same distance away from that star if it has a 365-day orbit. And a lot of these stars that the Kepler spacecraft is looking at are Sun-type mass or a little bit heavier, a little bit lighter, but the Sun is kind of an average star in some senses. Mass of the planet compared to Jupiter. Well, here we go. So here's Jupiter way up here, and of course the Jupiter-sized objects have more gravity and a little preferential for discovery by Doppler shift methods. We have to go down on the scale to get to the Earth-sized, and there are fewer Earth-sized than the larger ones for both the Kepler and for the radial velocity method. It's more, right now our technology is picking up larger planets rather than smaller, but we are detecting some Earth-sized planets. So habitable, potential habitable worlds, and we have here of sort of a list of exoplanets and the Earth and Venus over here on the side for comparison. So there are candidates for habitable worlds, and different telescopes are now being used to process the light from these exoplanets. As the exoplanet passes in front of its star, the atmosphere of the exoplanet will cause an absorption in the light from that star. And that's being analyzed now to look for water, look for oxygen, look for evidence of an atmosphere in the star. So it's a new sort of level of searching and looking for the characteristics of a planet that might be habitable. So last step here would be a law from the 1700s, I believe, Bode's law. And this law is just some interesting item that regards our solar system. So it's not a law in the sense that it has a theoretical basis behind it. It is a empirical law. It's just comes to be from analyzing the data of the orbits. This formula is the semi-major axis is equal to 0.4 plus n divided by 10. Now, for my students, you're not responsible for knowing this formula, and you won't have it on a test, but you should know the historical importance here. Bode's law does match the positions of the planets. So Mercury, Venus, let's do Earth. If we use n of 6, 0.4 and plus this should be should be 6, not quite. There's a little problem here. I've already divided this. This should be a 4 here rather than a 0.4. Sorry about that. So just scratch off that 0.4. We'll do that for you. So Bode's law, take 4 plus n and then divide by 10. So for Mercury, 4 plus 0 divided by 10 is 0.4 for its semi-major axis. For Venus, 4 plus 3 divided by 10, that'd be 0.7. For the Earth, the case I wanted to do, 4 plus 6 divided by 10, that's a 1 for its semi-major axis. So this continues through the solar system. It does predict a planet at the asteroid belt, so that's not correct. And it fails to predict correctly the position of Neptune, so that's not correct as well. But for the others, there's some interesting closeness in the result for the prediction of the semi-major axis for the planet and where it's actually observed. But it is not a law, and other solar systems don't follow this pattern. Computer models that simulate solar systems don't generate this pattern. It's just an interesting mathematical historical effect. So with that, I'm going to close this video and hope that you keep reading and asking questions.